Good morning, everyone. Today, we will be discussing an important topic: alternating current. We will take a look at the frequency response of a circuit containing a resistor, inductor, and capacitor in series, its maximum current, resonant frequency, and impedance. Let's get started. When combining a resistor and a capacitor in a series circuit, we can observe an alternating voltage applied to the circuit. This voltage is defined at any instant t as Vm sin Wt, where Vm is the maximum voltage and W is the angular velocity. The current I is inversely proportional to the time rate of change of charge Q on the capacitor, which in turn is determined by the capacitor's capacitance. This relationship is the foundation for understanding alternating current. I can be represented by equation 2, at any instant of time, where Im is the maximum value of the current and omega t plus phi is an angular rotation of the current. The concept of alternating current is a key part of electrical engineering, and it can be expressed in two equations. From equations 1 and 2, we see that the current leads the voltage by a phase angle, and this is demonstrated in the phasor diagram. This diagram is a visual representation of the vector of the alternating current. Understanding this concept is essential to mastering electrical engineering. Impedance is the opposition a CR circuit offers to the flow of alternating current, being measured in terms of a maximum current, Im, with the same units and dimensions as resistance. As such, having an understanding of impedance is essential to comprehend the behavior of current in a CR circuit. Vm is the maximum voltage applied to the circuit and omega is the angular frequency. Equation 1 states that V is equal to Vm times sin of omega times t. This equation illustrates the relationship between the applied voltage, inductance, frequency and time of the alternating current. Consequently, the current in the circuit depends on these variables, as well as the resistance of the resistor, and thus changes over time. In this slide we see the applied alternating current, or AC, EMF, which has an instantaneous value of V equals Vm times the sine of omega t. The current I at any instant of time t, is given by I equals Im times the sine of omega t minus phi. Lastly, Im is the maximum value of the current, given as I equals Im times the sine of omega t minus phi. The voltage in an alternating current circuit is lagging behind the electromotive force, as marked by the phase angle phi. This can be demonstrated mathematically with equations 1 and 2, in which the voltage or electromotive force will always lead the current by the same phase angle. This is exemplified in the phasor diagram of an LR circuit. An AC circuit consists of four possible components: resistor, capacitor, inductance and resistance. The EMF equation is expressed as equals 0 sin t, while the current equation is presented as I equals I0 sin t. In a circuit involving resistance, capacitor, inductor or a combination of the three, this allows for varying the current and EMF. In this slide, we explore an alternating current circuit with resistance, inductance, and capacitance components. We analyze the current in the circuit and the charge on the capacitor at any given moment. This complex relationship between these components and the current and charge demonstrate the importance of comprehensive understanding of AC circuits. slide I'm looking at presents the fundamental equation governing current in a series circuit composed of an inductor, capacitor, and resistor. This equation states that the net EMF of the circuit is equal to the current multiplied by the resistance within the circuit. This relationship, exemplified by Ohm's law, helps us to understand the current flowing in series circuits, which is key to the operation of devices such as electric motors. The current in a circuit is determined by an equation that involves a sinusoidal factor, making it possible for the current to vary rapidly at high frequencies. In one situation, the current is in step with the electromotive force, while in the other, the current is behind or in front of the EMF by an angle. This change of current along with the phase angle permits effective power sharing at any given point. Today we are talking about alternating current. We are discussing the LCR series circuit that has a very large capacitive reactance at low frequencies and a very large inductive reactance at high frequencies. At a particular frequency, the total reactance of the circuit is 0 and impedance Z is equal to R. This frequency is known as the resonant frequency of the LCR circuit. Let us learn more about this fascinating concept. The diagram illustrates the frequency response of an LCR circuit, with maximum current generated at its resonant frequency. The graph displays the changes in current in accordance to the alterations in frequency, delineating how the circuit reacts to multiple frequencies. At an LCR series resonance circuit, when the inductive reactance is equivalent to the capacitive reactance, the reactance of the circuit becomes 0, causing a maximum current flow in the circuit. Using this information, engineers can optimize the circuit to achieve optimal performance. An acceptor circuit, a series resonant circuit, is commonly utilized in radio and television applications. Its frequency can be adjusted precisely to identify the frequency of a preferred station by varying the capacitance and producing resonance. In a series LCR resonant circuit, if you want to increase the resonant frequency, then you need to increase the inductance, increase the capacitance, and decrease the impedance. Alternatively, if the impedance is too low, you can increase the inductance and the capacitance to achieve a higher resonant frequency. At resonance in an LCR AC circuit, the current and voltage might be in phase or out of phase. This depends on the proportion of inductance, capacitance and resistance in the circuit. Knowing how these components work together is necessary for predicting the effects of alternating current in an LCR resonance circuit. In series LCR circuits, resonance is observed at one frequency due to the fact that when inductive reactance and capacitive reactance are equal in magnitude and opposite in sign, the net reactance equals 0 and the current attains its maximum for that specific frequency. Electricity is generated in alternating current by the oscillation of a shifting magnetic field around a conductor, resulting in a more efficient and powerful energy than direct current. It is also used for power transmission, enabling the long-distance transfer of energy generated at one point of the grid to many other points. By using one power plant, energy can be provided to multiple locations. The power in AC circuits is determined by the product of the voltage and the component of the current that is in phase with the voltage, referred to as the power factor, which is related to the phase angle, phi. The instantaneous power is calculated by multiplying the maximum voltage, Vmax, and the maximum current, Imax, by sin 2 ohms Ft, where omega is the angular frequency and t is the time, so it oscillates between Vmax Imax and 0. Power factor is an important factor to consider when evaluating the efficacy of an electrical system. It is a ratio of true power, also known as active power, to apparent power. To express the power factor as a percentage, it is necessary to multiply the figure by 100. The ideal power factor is 1, which can be achieved by adding capacitance to an inductive circuit, thus enabling a reduction in the size of wiring and transformers. An LC circuit consists of an inductor L and a capacitor C, as shown in the figure. At time t equals 0, let Q be the charge on the capacitor. When the switch is closed, a current starts flowing. This creates oscillations between the inductor and capacitor, which oppose the current flow. Initially, the current increases exponentially, but it will eventually reach a steady state and the oscillations will dissipate. In an LC circuit, capacitors and inductors store energy as charge and current oscillate between the two components. This oscillation results in a transfer of energy between the capacitor and the inductor, depending on the current and charge at any given moment. As the oscillation continues, energy fluctuates between the components, giving rise to an alternating current. Electricity that reverses its direction in a cyclical pattern is called alternating current. Once the capacitor plates have been charged and the induced electromotive force is implemented, the current remains at a non-zero value. This continuous change in direction from positive to negative creates a wave-like structure, referred to as alternating current. As we can see, the circuit behaves as a simple harmonic oscillator, with the charge represented by Q equals Q maxcos, 2 pi Ft, and the current by I equals I maxon, 2 pi fort. This means that the voltage and current in the circuit oscillate between positive and negative values, forming a continuous cycle. Alternating current is a powerful energy source that oscillates between two components: a capacitor in its electric field, and an inductor in its magnetic field. This energy is highly efficient, as the total amount of energy must stay constant within the circuit. This energy can be used to power many different devices and technologies. This graph demonstrates how the electrical current and charge both oscillate in LC circuits. We can calculate the maximum value of current by considering the energy in both the inductor and capacitor must be equal. The LC circuit is a simple but powerful tool for controlling electrical and electronic energy flow. The LC circuit is composed of two components, the capacitor and the inductor, which are connected in an alternating current loop. When an alternating current flows through the circuit, the voltage across the capacitor and inductor will be equal. This is a result of the fact that the current across the LC circuit will always oscillate, making it a reliable and efficient way of controlling energy flow. The equation XC equals XL demonstrates a connection between the capacitance of a circuit and its inductance at a given resonance frequency. This frequency is figured out utilizing the given equation. By changing the capacitance and inductance of the circuit, it is conceivable to accomplish a desired resonance frequency. Answer. Apparent power is the product of true power and apparent root mean square current, which is often used in electrical networks for efficient transformation and regulation of voltage. Alternating current is a type of electrical current that alternates its direction of flow in a circuit. It has two components. True power, which is the actual amount of power delivered to the load, and apparent power, which is the power supplied by the source. The ratio of true power to apparent power is referred to as the power factor. Among the choices given in the slide, the answer to the question is power factor. A transformer is an electrical device which takes in alternating current and outputs another alternating current of a different voltage, enabling us to control and manage power supply. It is a crucial part of the electrical grid, ensuring that the appropriate voltage of electricity reaches the desired locations. A transformer is a device that allows us to convert low alternating current with high voltage into high alternating current with low voltage and vice versa. It can also take electric current from one circuit and transform it to a different circuit while maintaining the same frequency. It is a valuable tool to have in any power-related toolkit. A transformer is a pivotal piece of equipment in present-day electric systems. It operates by using mutual induction, where two sets of coils, wrapped around a gentle iron center, enable the flowing of voltage from the primary coil to the secondary coil. The current flowing through the primary coil generates a magnetic flux which, in turn, influences the secondary coil and creates an electromotive force, which, ultimately, transfers the voltage. This device is of great benefit in electricity distribution, aiding in the reliable and practical transportation of electricity from the source to its destination. The physics term alternating current is based on an exchange of energies between two systems. According to Faraday's second law, the induced electromotive force or voltage in the secondary coil with N's turns is given by the equation V equals N's x def, delta T. Additionally, The alternating flux produced in the secondary coil also causes a back electromotive force in the primary coil, E flat equals Np x d delta T, where Np is the number of turns in the primary coil. Combining these two equations results in a formula for the input voltage and output voltage, Vp equals Ns per Nepper by Vs. This formula demonstrates how mathematics can be used to interpret and explain the behavior of physical phenomena. When looking at the transformation of electrical power, alternating current, AC, is far more efficient than direct current, DC. The transformer ratio, the ratio of the number of turns in the secondary coil to the primary coil, is critical to the successful conversion. This is why AC is needed for this process, since ideal transformers cannot be used with DC voltages, as they are based on Faraday's law. The equation of voltage times current in the secondary must equal voltage times current in the primary must be maintained for an efficient transformation of power from one circuit to the other. When talking about alternating current, step-up transformers are an efficient way to increase voltage. These are used to convert a low AC voltage into a high AC voltage, making them an effective way to transfer current over long distances. Step-up transformers offer a safe and convenient way to increase voltage and ultimately increase power. This slide shows a step-down transformer, a device that converts a high alternating current voltage into a lower voltage. It is essential in the efficient transmission of electricity over long distances, reducing the voltage to remain safe and efficient. It helps to ensure that the electric power we use is safe and reliable. Alternating current is an electrical current that reverses its direction and magnitude cyclically. This type of current is used in a range of electronic devices, from simple devices like a light bulb to complex systems such as computers. The output power in an ideal transformer should be the same as the input power, giving it an efficiency of 100%. In reality, the efficiency may not be 100%, but it is still a basic principle to follow. Energy loss in transformers is caused by flux leakage, whereby not all of the flux from the primary passes through to the secondary as a result of poor design or air gaps in the core. To reduce this loss, winding the primary and secondary coils one on top of the other is recommended. Windings used in alternating currents have resistance, which results in energy loss due to heat production in the wire, proportional to current and resistance. To minimize losses in high current windings, thicker wire could be used. Furthermore, when alternating magnetic flux induces eddy currents in an iron core, core heating can occur. To reduce this effect, a laminated core can be employed. Magnetic hysteresis is a significant consideration when dealing with alternating current. Optimal performance can be ensured by selecting materials with reduced hysteresis loss, thus lowering the amount of heat generated in the core. This in turn reduces energy expenditure and optimizes operation. A step-down transformer is employed in a 6 volts bed lamp due to its ability to reduce or step down the electric voltage from a higher to a lower level. It is noteworthy that this voltage stepping down is done in a regulated fashion for safety and efficacy purposes. Alternating current, or Wattles component of current, is a kind of electrical energy that flows in reverse direction periodically. Generators and power transformers are machines that produce this type of energy, which can be used to power machines, lighting, and other electronic devices. It is an essential part of many modern applications. Power factor in an LCR series circuit is unity when the phase difference between voltage and current is zero, meaning voltage and current have the same phase. This results in volts and currents being in phase and a power factor of 100%, thus indicating an ideal circuit. Transformers play a pivotal role in electrical systems. They allow us to change the voltage of alternating current so it can be used in a variety of applications. In this case, we can see that transformers are used only in AC circuits, meaning that current with alternating voltage. This slide is about alternating current and the EMF across the secondary of a transformer. The magnitude of the EMF across the secondary does not depend on the number of turns in either the primary or the secondary, nor does it depend on the magnitude of the EMF applied across the primary. Rather, it only depends on the resistance of the primary and the secondary. Transformer ratio, in an ideal transformer, is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. This ratio determines the voltage output of the transformer. Generally, the higher the voltage in the primary winding, the higher the voltage in the secondary winding.